All right, guys, so we're going to finish off the unit with lesson 5. So this is the last part of the chapter. So in this lesson, we're going to be looking at being able to use the normal distribution to approximate the binomial distribution. So for this, you're going to kind of need to go back and, we're going to need to kind of refresh ourselves on some of the concepts of the binomial distribution, which was in the last chapter. So it was chapter 5. So our goal is to be able to use the normal distribution to be able to compute probabilities for the binomial variable. So that is what we want to do. In this case, we're going to review the binomial distribution. All right, so let's go ahead and review binomial. So in a binomial experiment, remember that binomial means bi means 2 and nomial means name or category. So that means that you only have 2 outcomes, either success or failure. If you want to calculate the probability of a binomial variable, then you're going to use the formula in 5.3, which is given below. So remember that this is the Cx is the combination, n is the number of trials, and so on. So we're going to use this formula in the following example just to kind of refresh ourselves on binomial. So a survey found that 30% of teens received their spending money from part-time jobs. If 100 teenagers are selected at random, find the probability that 10 of them will have part-time jobs. So for part A, we want the probability that x is equal to 10, because we want 10 of them to have part-time jobs, so probability. So we're going to use a combination. So n is 100 in this example. We have 100 teenagers, and we're choosing 10 of them to have part-time jobs. And then we're going to multiply that by the probability of success. So it says 30% of teens, get their money from part-time jobs. So that's our probability of success. Our probability of failure is 1 minus the probability of success, which is 70%, 0.70. So now we have our p is 0.30. You're going to raise that to the 10th power. Now you have 0.70 raised to the n minus x power, so raised to the 100 minus 10 power. All right, so you do that, and you get a number from that. So I'll do that on Desmos real quick. So we'll do that here. Let's give ourselves some room. Okay. So we're going to do combination. Multiply by that raised to the 10th. And then that raised to the 90. So we got this probability, which is very small, 1.17 times 10 to the negative 6. Okay, so a very small chance that only 10 of them will have part-time jobs out of 100. So very small. That's that's 0.0000017. So very small. All right. So now for part B, we need to find the probability that at least 60 have it. So x is greater than or equal to 60. So that means that we got to do this for 60, 61, 62. We got to do it for 62. We got to do it for 63, all the way to 100. That's a lot of numbers to put in. Even if you were to use the binomial table, that's still a lot of numbers to add up together. So there's a problem here, right? The problem is with using binomial probability is that when n is large, the calculations are quite difficult to do by hand, all right, as we just witnessed right here. So because of that, sometimes we can approximate what the probability is using a normal distribution. All right, if you would like to do that instead of having to do all these numbers, then in that case, if you need to do them by hand, a normal distribution will actually benefit you. So when can we use it? So you can only use it as long as the following situations occur. So the probability of success P has to be about 0.5. So as the number of trials increases, so the P has to be about 0.5. The N has to be, relatively large. So as N increases, the shape becomes closer to the bell curve. So the larger the N, the closer the P is to 0.5. Then the more similar the binomial distribution is going to be to the bell curve, right? So when P is close to 0 or 1, which means it's not 0.5, that in N is small, then that means that you can't use the normal approximation. You can't use the bell curve to make the calculation. You're going to have to do it by hand, or like you're going to have to do all those numbers, or do it on the computer or something like that. All right, so we're going to summarize this in one condition, in a couple conditions. Okay, so in order to take into account the P is 0.5 and the N being large enough, this is what we're going to be using. Okay, so we're going to focus on this. If we've satisfied these two criteria, then we're good. We can go ahead and proceed with using the normal distribution. The reason why we wanted to use a normal distribution is much simpler because you have to calculate the z-score and then just get the probability from the probability table. So simplifies the steps to doing it immensely, and this is why we prefer using the normal distribution. All right, so we're going to go ahead and do a problem in a little bit that involves this condition. All right, so in addition to this condition, so if you use this condition, then you can go ahead and use the normal approximation. However, in order to use the normal approximation, you have to correct for continuity. And what do we mean by that? So correction for continuity means that you're making a correction because remember that the bell curve is continuous, but the binomial is discrete. You're dealing with whole numbers when you're dealing with binomial. Like the number of times you get heads, 1, 2, 3, 4, 5. Those are countable numbers, so binomial tends to be discrete. Whereas this, normal distribution tends to be continuous. This should say continuous. All right, so because of that difference between those two categories, we need to apply a correction factor. So in order to do that, we're gonna need the boundaries for that number. Remember the class boundaries whenever we did the frequency tables. So whenever we did the frequency tables, we used the 0.5 rule. So we're gonna use that pretty much here. So if you have 8, then your boundaries would be 7.5 to 8.5. You're going to take away 0.5 to 8, add 0.5 to 8, and that's how you get your two boundaries. So that's the 0.5 rule that we talked about whenever we did frequency distributions. We actually talked about it last section too, because we needed that to make the histogram. Okay, so some examples of using the correction factor. So for x is equal to 8, the correction is so we're going to use the boundary. So we said it was going to be 7.5 to 8.5. So that means that we're going to rewrite this using the notation. So that means x has to be between 7.5 and 8.5. Now for x is less than or equal to 7. So if you wanted to do less than, then the rule is that you're going to add 0.5 to the 7, okay? So that means it's going to be 7.5. So if it's less than, you're going to add 0.5 to the number. If it's greater than or equal to, then you're going to take away 0.5. Okay? So for x is greater than or equal to 3, the correction is going to be 6 or greater than or equal to 3. Then it's going to be, that means you're going to take away 0.5. So that means it's going to be 2.5. All right, so which means that whenever we write the probability, it's going to be the probability that x is less than or equal to 7.5. And then for this one is probability that X is greater than or equal to 2.5. All right, and that's the correction factor to correct for continuity. All right, so we're going to, so this little graph is basically a summary. So this is a table to summarize what I was just talking about, and this is an example of, you know, a histogram, a binomial distribution actually resembling a normal distribution based on the fact that the conditions work out. So like the probability is high enough and the number of trials is high enough that we can approximate. All right, so then the table below summarizes what we said. So if it was greater than, you take away 0.5. If it's less than, you add 0.5. Okay, so so this is the summary, like we said, of how, you know, what to use. So I'll give you some examples. So like, for example, if you were to do, let's look at x equals to 2. So if you had x equals 2, right? So if you had x equals 2, that would mean that, so we're gonna do the boundaries for x equals 2, right? So that would mean that you want a little bit before the 2 and you want a little bit after the 2 if you want it to equal to 2. So that means you want to subtract 0.5 from 2. And, you know, you want to add 0.5 to 2. So that will give you 2.5. And this will ensure that you have x is equal to 2 because that is right in the middle of this range, right? So when you have x equal to 2, then you're going to take away 0.5 and add 0.5. That's what this rule is saying. Now, if you were to do greater than or equal to 2, right? So if you want it to be greater than or equal to 2, well, you're going to use the class boundary. You're going to use the boundaries here, right? So if you want it to be greater than or equal to 2, that means that you want it to make sure that you have 2, right? So, which means that, and you want bigger, so that means you want 2.5, or I'm sorry, so you want to make sure that you include 2. So like, think about it like this way. So if this were 2 on the number line, right? And you want greater than, so you want this side, and you want it to be equal to, then what you got to do is you have to take a little bit before the 2 and then go from there. That way this ensures that you actually have 2 in your data set. So whenever you have greater than or equal to 2, you're going to take away 0.5. So then you're going to use the 1.5 number here. This will ensure that you have all the, you know, all the numbers, you know, including the 2. Now when you want greater than 2, things change. So if you want greater than 2, then that means you're no longer including the 2, right? You only want greater than, which means in order to ensure that you do not get 2, you do not want to use the 1.5. You want to use the 2.5 number, okay? And this will ensure that you have the numbers greater than 2, but not equal to 2. So you don't want to be close to 2. So this is why you use the 2.5 number, okay? So this is why you add 0.5. So with less than or equal to 2, again, you want, you can equal to 2, but you want less than 2 as well. So in order to ensure that you have 2, just take a little bit after it and then do it to the left, right? That way you ensure that you have 2. Because remember, you're correcting for continuity, so there's going to be a little bit error, which is why you want to go a little bit above the 2 to ensure that you actually have it to correct for it. So therefore, you're going to use the 2.5 number. So less than or equal to. And then, you know, if you want less than 2, then, you know, in that case, you don't want it to be equal to 2, you just want it to be less than. So what you would do is, well, to ensure that you don't have equal to 2, then you just take a little bit before it and then go to the left. And that will be the 1.5 number. Okay, and that's basically how that works. If you want to think about it logically like that, you can, or, you know, you can just use the correction table. But I wanted to kind of explain, you know, why these numbers are the way they are. All right, and then they give you the formula for the mean and the standard deviation because you're going to need that. I actually copied that formula below as well. So if you wanted to use this in word problems and applications, then you want to use the following procedure. So the step one, you want to check to see if you can use the normal approximation. Again, you're gonna, for that step, you're going to figure out, you're going to determine whether or not, let me erase this real quick. Okay, so you're going to determine whether or not n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Okay, and then for step 2, you're going to find the mean standard deviation. You know, again, I provided the formula here just in case you forgot it. Write the problem in probability notation using x. So, you know, for example, you know, is it x is greater than 2.5, you know, what is it, right? Or if it is x greater than 2, for example, greater than or equal to. And then if you want, then rewrite it using the continuity correction factor. So in this case, you're going to correct for it. And in this case, it's going to be greater than or equal to. Since you want greater than 2, you're going to correct for that and do 1.5, for example. All right? And that will be using continuity correction. Show the corresponding area under the normal distribution. That's when you actually, you know, draw it out. And then you want to shade. So this is the 2, and you're going to correct for that and do here. Oops. So if 2 are here, then 1.5 will be here. So you can do that and then correct for it and do to the right. And then you're going to find the z values. Again, you're going to use the z formula. Okay, using the sigma that you did there and the mean that you did there in step 2. And then find the solution. You know, finding the solution means, you know, using the z table. So you use the z table. Okay, so let's show you how this works. So number 2, a magazine reported that 6% of American drivers read the newspaper while driving. So not a very safe thing to do, but thankfully it's only, you know, 6% of people that do that. So if 300 drivers are selected at random, find the probability that exactly 25 say they read the newspaper while driving. All right, so step 1, check to see whether the normal approximation can be used. So we're going to be checking these guys. So n is 300 in this example. P, the probability of success, is 0.06. The probability of failure is 1 minus 0.06, which is 0.94. Okay, so that's that guy. So Q is 0.94, P is 0.06, N is 300. Now we're going to plug it in. So 300 times 0.94. And we're going to calculate that number. So that's going to be 94 times 3, which is 12, carry the 1, so about 282. All right, I'll double check that on the calculator now. Okay. Okay, so 282. And then now and that is definitely greater than or equal to 5, so that checks out. Now we want 300 times point. That's for the NQ. Now we're going to do the NP. 0.06, which that's going to be, 18, which is greater than or equal to 5, so that checks out. All right, so that means we can proceed. So in step 2, find the mean of standard deviation. So we're going to use the formula for the mean. which we already calculated that. That was, the 300 times 0.06, which is 18. The standard deviation is square root of NPQ. So 300 times 0.06 times 0.94. Get what that number is now. All right, so that's 300. Let's do square root. So 4.11, just about. All right, so that's our standards. That's step 2. Step 3, write the probability and probability notation. So probability, they want probability that exactly 25. So x equals 25. We write it using the current continuity correction. So now we want to do the boundaries. So use the 0.5 rule. Take away 0.5 and then add 0.5. So that's what we want. Show the corresponding area under the normal distribution. So we're going to draw the normal distribution. Okay, hold on. Okay, and we're not going to be, too detailed with this curve. We're just going to, just label the mean. Mean is, excuse me. So the mean is 18, and we know we want it to be 25. So standard deviation is about 4. So 25 is around here. We're just gonna approximate. We're not gonna, be too specific with it. So this is 25. And we're doing 24.5. So 24.5 is around there. And 26.5 or 25.5 and 24.5. All right, and then we're gonna shade in between those, and that is the area that we're looking for. So that little bitty area is gonna give us a probability for 25. All right, so find the corresponding z values. So we're gonna calculate 2 z values here. So we got z1. So we have x minus mu, so we have 24.5 minus the mu, which is 18, over the standard deviation 4.11. We're going to get that, and then we're going to do the z2, 25.5 minus 18 over 4.11. So we're going to get those 2 values. We got 1.58, so 1.58 and 1.58, 1.82. Okay, so those are our 2 values. So find the area using the table. So again, since we're finding the area between 2 things, right, probability that z is between 1.58 and 1.82, then we're going to subtract for 1.82 and minus the value for 1.58. So we're going to look this up on the z table twice, right? 2 places, and get those values. All right, so we're going to look up those values. So let's look up let's look up 1.82 on the z chart, the standard normal probabilities chart. So 1.82, it's right here. So 1.82. So 1.9656 So we got 0.9656. So let's write that down. Next number is 1.58. So we got 1.5012345678. So 0.9429. Okay, so it's going to be 0.0. 0.01. 2.7. I believe that's what it is. I'll double check that. Okay, 0.02227. Right, that's why I wanted to double check because it seemed a little bit off. Okay, 0.0227. There you go. All right, 0.0227. So that is the probability of finding exactly 25 people that say they read the newspaper while driving, which, thank goodness, that is a small percentage because I do not want to run across those people if they're reading the newspaper and I'm driving with them on the same road. So there's that. All right, so number 3. 10% of Americans are allergic to ragweed. If a random sample of 200 people is selected, find the probability that 10 or more will be allergic to ragweed. Again, this is a binomial because you're either allergic or you're not. So there's only 2 outcomes here, and if you select these people, they're completely independent from one another. So there's tons of reasons why it's binomial. But we have a large sample size, so let's see if that works. So step 1, we will see if the conditions hold out. So n is 200, p is 0. It says 10%, so we're going to say success is being allergic, even though that's not a good thing, but we'll call that success. And then failure is 1 minus 10, which is 90%. So 0.90. So we got 200 times 0.10, which is, excuse me, so in this case, 10% of 200 is 20, and then which is greater than or equal to 5, so that checks out. And then we have 200 times 0.90, which is 180, which is greater than or equal to 5, so that checks out. Step 2. So according to the steps, right, we want to find the mean and all that stuff, and then write the probability. So mu is, we already calculated it, is 200 times 0.10, but I'll write it out. Standard deviation, square root, 200 times 0.10 times 0.90. I'm going to calculate that since it is a square root after all. .24. All right, step 3. Write the probability in notation. So we want the probability that 10 or more, so greater than or equal to 10. Step 4. Write it in terms of the continuity correction and then graph it. So greater than or equal to 10. So that means that, and you can use a table for this, but I like to think through it. So 10 here, and you want equal to 10, and you want greater than 10. And so in order to make sure that you actually have 10, you're going to take a little bit before that and then do it from there. Okay, so 9.5. So I know that this is going to be greater than or equal to 9.5, and that'll be my correction factor. Again, if you didn't, if you don't remember that, then just go to the correction factor. If you want greater than or equal to, take away 0.5. So 10 minus 0.5 is 9.5. All right, so now we got the correction factor. So let's do, oh yeah, actually we need to graph it, right? So let's graph it. Just do a quick graph here. So the mean is 20, and we want greater than or equal to 10. So, so 10, pretty small. So around here. So we'll say that's 10. We want greater than, so we are doing 9.5 here, and we want greater than that. Okay. All right, just gonna do this. I'm just gonna mark the 10, but I'm not gonna actually, put it yay high. So 9.5 and on is what we want. All right, so now step 5, we're gonna calculate the z's. Here we only have one z value since there's only the 9.5. So we got 9.5 x minus mu, 9.5 minus 20, that's our mean, 20, divided by the 4.24 that we got. And that'll give us our z-score. We want to round it to 2 decimal places. All right, 9.4 minus 20. So, oops, I got negative 2.5. All right, I like to double and triple check, so let me, okay, so that it works out. Oh, wait, see, this is why I like to double triple check. This is supposed to be 9.5. Negative 2.48. Okay, so negative 2.48. Does, those little numbers make a difference, so let's make sure we adjust that. All right, step 6, now we're gonna find the solution. So we want the probability that z is greater than or equal to negative 2.48. Remember, since we want the area to the right, the table by default gives us the left side. So we need to find the right side by subtracting from 1. So, okay, so we need 1 minus the probability that for less than, for the left side, and then that will give us our answer. So we're going to look up to negative 2.48 on the table. So that's negative 2.48 is 0.0066. All right, 1 minus that, so it's going to be 0.9934. All right, and that's your answer. So 99% chance of finding 10 or more people that will be allergic. So, 10 or 11 or 12, and so on. Okay, so now we're going to look at the last problem here. So if a baseball player's batting average is 0.32 or 32%, find the probability that the player will get at most 26 hits in 100 times at bat. So we know n is 100. Probability of success of, hitting the ball with the bat, 0.32. We want, or probability of failure is 1 minus that, which is 68%. All right, so step 1. Okay, so step 1 is to actually use the requirements. So we got to do 100 times 0.32, which is, let's calculate that. That's equal to 32, which is greater than or equal to 5. 100 times 0.68 is 68, which is greater than or equal to 5. So that checks out. Step 2. So step 2, you want to calculate the mean and standard deviation. So the mean is 32. We already calculated that earlier. Standard deviation is square root of 100 times 0.32 times 0.68. We already know that 100 times 0.32 is 32, so we got to do 32 times 0.68, and then take the square root of that. .66. All right, so step 3. So we're going to write out the probability. So we want at most 26, which means the most we have is 26. So that we want less than or equal to. So x is less than or equal to 26. Step 4, correction factor and graph. So since we want less than or equal to 26, so we want 26, we want it to be equal to, and we want less than. To make sure that we have 26, we're going to take a little bit over here and then do less than to ensure that we have 26. So therefore we will use 26.5. So x is less than or equal to 26.5. Or you can use the table and that'll tell you what to add or subtract. Now we can graph it, just a quick graph. Mean is 32, 20, let's say 26 is over here, and then 26.5 is there. So then we want less than or equal to. So there you go. Step 5, we are going to calculate the z-score. We only have one z-score to do, is 26.5. Minus the mu divided by the standard deviation that we found over here. Okay, calculate that number. So this should say 4.66 just to be safe. So negative 1.18. All right, so now we got step 6, which is find the probability. So the probability that z is less than negative 1.18. So we want less than, so that means we just look up the table and that is it. We don't have to subtract from 1 or anything. So let's look up the table real quick. Negative 1.18. 0.1190. So 0.1190. All right, let me verify that. 0.1190. Okay, so there you go. All right, and that's all there is to it, guys. So you just have to follow the steps. You know, recall how to calculate the z-score. The hardest part is the correction continuity. So you just got to remember that, you know, that correction factor. And, you know, once you do that, everything else is pretty much the same. All right, guys. So good luck on this and keep studying. I'll see you later.